हेलो दोस्तों, I welcome you to explore our today's topic सर्कुलर मोशन। सर्कुलर मोशन समझने के लिए हमें 11th फिजिक्स के कुछ बेसिक क्वांटिटीज का आना जरूरी है, जैसे डिस्प्लेसमेंट एंड वेलोसिटी। So let us start the first quantity, displacement. What is displacement? Displacement is the shortest distance from initial point to final point. For example, अगर हमें घर से कॉलेज जाना है तो we have two routes. One is the long cut, another is the short cut. अगर हम लोग long cut से गए तो what is the total distance traveled? 1 kilometer up, then 2 kilometers east and 1 kilometer down. So total becomes 4 kilometer. और अगर हम लोग short cut से गए तो what is the total distance traveled? 2 kilometers east. If I ask you the question, what is the displacement if I go from home to college? Is it the 4 kilometer by long route or is it the 2 kilometer by short route? The answer is displacement is 2 kilometers east. Displacement is 2 kilometers east from initial point to final point. Coming to the second quantity, which is velocity. Velocity is the rate of change of displacement. Formula wise, velocity equals displacement upon time. What is the displacement when I go from home to college? 2 kilometers. Hence we substitute the value of displacement as 2 kilometers. And the time taken, let us say, to go from home to college is 1 hour. So what will be the time taken? Time taken will be 1 hour. So the velocity becomes displacement upon time, which is 2 kilometers upon 1 hour, which is 2 kilometers per hour in each direction. So these are the two quantities which we should be familiar to start with the circular motion. Continuing further with analogy between linear quantities and angular, that is circular quantities. So what is analogy? Analogy means इसकी टॉपिक उसके साथ means जहां हम लोग को linear displacement x दिखे वहां हम लोग angular displacement थीटा डाल देंगे। जहां हम लोग को linear velocity v दिखे वहां एंगुलर वेलोसिटी ओमेगा डाल देंगे। जहां हमें लीनियर एक्सेलरेशन a दिखे वहां एंगुलर एक्सेलरेशन अल्फा डाल देंगे। That means wherever we have linear displacement x, we will substitute with angular displacement theta in circular motion. Wherever we have linear velocity v, we will substitute with angular velocity omega. Wherever we have linear acceleration a, we will substitute with angular acceleration alpha. मैं एक बार फिर लिख देता हूं, linear displacement x is analogous to angular displacement theta. Linear velocity v is analogous to angular velocity omega. Linear acceleration a is analogous to angular acceleration alpha. जहां जहां linear displacement theta हो वहां पे हम लोग को सर्कुलर मोशन में एंगुलर डिस्प्लेसमेंट थीटा डालना है। जहां जहां लीनियर वेलोसिटी v है वहां सर्कुलर मोशन में एंगुलर वेलोसिटी ओमेगा। जहां जहां लीनियर एक्सेलरेशन a है वहां सर्कुलर में एंगुलर एक्सेलरेशन अल्फा। ये हम लोग को रट लेना है। नाउ हाउ डू वी यूज दिस एनालॉजी? इफ वी रिमेंबर द फॉर्मूला फॉर लीनियर वेलोसिटी, इट इज डिस्प्लेसमेंट अपॉन टाइम। वेलोसिटी इक्वल्स डिस्प्लेसमेंट अपॉन टाइम। सिमिलरली सर्कुलर मोशन में हमारे पास क्या होगा? एंगुलर वेलोसिटी इज इक्वल टू एंगुलर डिस्प्लेसमेंट अपॉन टाइम। लीनियर वेलोसिटी इज इक्वल टू लीनियर डिस्प्लेसमेंट अपॉन टाइम। एंगुलर वेलोसिटी इज एंगुलर डिस्प्लेसमेंट अपॉन टाइम। वेलोसिटी v इज इक्वल टू डिस्प्लेसमेंट x अपॉन टाइम। एंगुलर वेलोसिटी ओमेगा इज इक्वल टू एंगुलर डिस्प्लेसमेंट अपॉन टाइम। जहां हमारे पास वेलोसिटी है वहां सर्कुलर मोशन में है एंगुलर वेलोसिटी ओमेगा। जहां हमारे पास लीनियर डिस्प्लेसमेंट x है वहां है हमारे पास एंगुलर डिस्प्लेसमेंट थीटा एंड टाइम रिमेन्स सेम। कमिंग टू द नेक्स्ट क्वांटिटी, लीनियर एक्सेलरेशन। लीनियर एक्सेलरेशन a, इसका फॉर्मूला हमें पता ही है, चेंज इन वेलोसिटी अपॉन टाइम। फाइनल वेलोसिटी माइनस इनिशियल वेलोसिटी अपॉन टाइम। सिमिलरली एंगुलर एक्सेलरेशन अल्फा becomes change in angular velocity upon time. That is alpha equals final angular velocity minus initial angular velocity upon time. Instead of linear acceleration a, we have angular acceleration alpha. Instead of final velocity v, we have final angular velocity omega. Instead of linear initial velocity, we have initial angular velocity omega naught, and time दोनों में same ही रहेगा. So acceleration is v minus u upon t. Similarly, angular acceleration is omega minus omega naught upon t. So this is the concept of analogy between linear quantities and circular or angular quantities. Continuing further with our analogy means इसकी टोपी उसके सर concept. Wherever we find linear displacement x or linear displacement s, x and s are both the same symbols for linear displacement. जहां भी हमें linear displacement x या s दिखाई दे वहां हम लोग angular displacement थीटा डाल देंगे. जहां भी हमें linear velocity u दिखाई दे वहां हम लोग angular velocity initial ओमेगा नॉट डाल देंगे. जहां भी हमें linear final velocity v दिखाई दे वहां final angular velocity ओमेगा डाल देंगे. जहां हमें linear acceleration a दिखाई दे वहां angular acceleration अल्फा डाल देंगे. उससे we have the analogy between linear motion and circular motion. Velocity is equal to displacement upon time. उसके बदले velocity के बदले we have angular velocity. Displacement की जगह पे we have angular displacement. Velocity is displacement upon time. Angular velocity is angular displacement upon time. Acceleration is change in velocity upon time. Acceleration के बदले we have angular acceleration, which is change in angular velocity upon time. Instead of final velocity, we have final angular velocity. Instead of initial velocity, we have initial angular velocity. So acceleration is v minus u upon t becomes angular acceleration is omega minus omega naught upon t in circular motion. Similarly, इसको अगर हम लोग क्रॉस मल्टीप्लाई करके रीअरेंज करेंगे, we get our first kinematic equation v is equal to u plus at, which in circular motion transforms to v के बदले final angular velocity, u के बदले initial angular velocity, acceleration के बदले initial angular acceleration. So v is equal to u plus at becomes omega is omega naught plus alpha t. Second kinematic equation, v square is equal to u square plus 2s becomes omega square is omega naught square plus 2 alpha theta. Final velocity के जगह पे final angular velocity, initial velocity के जगह पे initial angular velocity, acceleration की जगह पे angular acceleration, displacement की जगह पे angular displacement. So v square is equal to u square plus 2s becomes omega square is omega naught square plus 2 alpha theta. The third kinematic equation, s is ut plus half t square transforms to theta is omega naught t plus half alpha t square. Using the same things, linear displacement s के जगह पे we will have angular displacement theta. Initial velocity के जगह पे यहाँ पे रहेगा initial angular velocity. Acceleration के जगह पे we will have angular acceleration alpha. So s is ut plus half t square transforms to theta is omega naught t plus half alpha t square. So these are the three kinematic equations in circular motion. Now let us understand our next concept, relation between linear and angular quantities. From maths, we know that s is r theta, where s is arc length, r is radius of the arc, theta is the angle subtended by the arc at the center of the circle. We know this relation s is r theta. So I am writing the same relation s is r theta. Now in physics, s denotes displacement and x also denotes displacement. So instead of s, I am writing x. So x is r theta. This is our first relation between linear, that means linear displacement, and angular, that means angular displacement. So linear displacement x is radius into angular displacement theta. This is our first relation. Dividing this equation by time t, we get displacement upon time is equal to radius into angular displacement upon time. But displacement upon time is nothing but velocity. Velocity is displacement upon time. And angular displacement upon time is nothing but angular velocity. From this relation, angular velocity is angular displacement upon time. Therefore, displacement upon time is radius into angular displacement upon time becomes velocity is radius into angular velocity. Going further and again dividing by time t, we get velocity upon time is radius into angular velocity upon time. Velocity upon time is nothing but acceleration, and angular velocity upon time is nothing but angular acceleration. From this relation, acceleration is change in velocity upon time, angular acceleration is change in angular velocity upon time, considering the initial velocity and initial angular velocity to be 0. Hence we get our new relation, the third relation, which is acceleration is radius times angular acceleration. So these are the three relations which we need to remember. S is r theta or x is r theta. This is the first relation. Second relation, v is r omega. Third relation, a is r alpha. I am writing all this in this tabular form. X is r theta, v is r omega, a is r alpha. If we take these relations and write them in vector form, we get linear displacement x is angular displacement theta cross product with radius r. Linear velocity v is equal to angular velocity omega cross product with radius vector. Linear acceleration a is equal to angular acceleration alpha cross product with radius vector. The derivation of these three we'll see in our next section. So are these three relations clear? X is r theta, v is r omega, a is r alpha. In vector form, it becomes reverse. X is equal to theta cross r, v is equal to omega cross r, a is equal to alpha cross r. This table and this table are almost same, except that we have reversed the angular quantities and radius. So this is the relation between linear quantities and angular quantities. Let us now see the derivation of v is equal to omega cross r, our second relation. Starting with s is r theta, we get ds is equal to d theta cross r from the relation s is theta cross r. Writing it in the form of del s is equal to del theta cross r. Dividing by small time interval del t, we get del s upon del t is equal to del theta upon del t cross r. But velocity is del s upon del t, small displacement upon small time, and angular velocity is del theta upon del t, small angular displacement upon small time. Therefore, we can rewrite this equation as v is equal to omega cross r. Del s by del t we substitute by v, del theta by del t we substitute by omega. Hence, we have successfully derived this relation v is omega cross r. Similarly, we can derive our third relation a is equal to alpha cross r by using the same steps. Moving on to the classification of circular motion. Circular motion is broadly classified into uniform circular motion and non-uniform circular motion. Uniform circular motion refers to circular motion with constant angular velocity. Uniform circular motion refers to circular motion with constant angular velocity. Example, motion of hands of clock. घड़ी के कांटे का चलना. घड़ी का कांटा कांस्टेंट एंगुलर वेलोसिटी के साथ गोल गोल घूमता है. Similarly, motion of earth about the sun is with constant angular velocity. Hence, these two motions are coming under uniform circular motion. Coming to non-uniform circular motion. Non-uniform circular motion means circular motion with varying angular velocity. Non-uniform circular motion means circular motion with varying angular velocity. Varying means either increasing or decreasing angular velocity. For example, whirling of stone. When we take a stone and tie it through a thread and whirl it in circular motion, at each point the velocity goes on changing. At highest point the velocity is lesser, and as the stone goes down the velocity goes on increasing. As the stone goes down, the velocity increases. As the stone goes up, the velocity decreases. As the stone goes down, velocity increases. As the stone goes up, velocity decreases. Hence, this is an example of varying angular velocity. Similarly, the motion of fan. When we just switch on the fan, the velocity goes on increasing. The angular velocity increases when the fan is switched on. Similarly, when we switch off the fan, the angular velocity decreases gradually. Hence, these are examples of non-uniform circular motion. Further, classifying circular motion into horizontal circular motion and vertical circular motion. As the name suggests, horizontal circular motion means circular motion in horizontal plane, and vertical circular motion means circular motion in vertical plane. The example of horizontal circular motion is merry-go-round, which goes in horizontal circle. The example of vertical circular motion is giant wheel moving in vertical circular motion. So this is the classification of circular motion. Let us now understand the conditions for circular motion. The condition for circular motion is centripetal force must be perpendicular to velocity at all times. First, let us understand what centripetal force means. Centripetal word can be broken into two parts. Centri referring to center, petal referring to towards. Thus, centripetal refers to towards center. Hence, centripetal force refers to force towards center. Let me again explain. Centripetal force means force towards center. Now, let us further understand this centripetal force by an example. Let us consider this box which I want to move in circular motion. For that, let us say the box was moving in this direction with some velocity v. I apply a force with the marker with my hand in a direction perpendicular to the velocity. The velocity is in this direction. The motion of the hand or the muscular force of the hand is perpendicular to the velocity. Muscular force is in vertical direction, velocity is in horizontal direction. So let us see what happens if I apply muscular force on this box. The box has moved to this new position. Now its velocity will be in this tangential direction, and I will apply a force perpendicular to the direction of velocity. The velocity is in this direction, my force will be in perpendicular direction. So now the box, this is the new position. Now the velocity of the box is in vertical direction, vertically downward. I apply again a muscular force in a perpendicular direction. The box is moving like this and I apply force in horizontal direction. Again, the position of the box is now like this. Now the box is moving in tangential direction in right direction. Again, I apply a muscular force in the perpendicular direction. So again, the box position will change and the box will have a velocity in vertically upward direction. I will again apply a force in perpendicular direction. So this is the direction of velocity of box and I apply a force in a perpendicular direction. So if you see carefully, the box has moved in circular motion. From this position, it has moved successfully back to the same position because the force was always perpendicular to the velocity. This is what we are seeing here. This is the box and it is having a velocity v. We are applying the muscular force by our hand. The force and the velocity are perpendicular. Hence, the new position of the box with the velocity v in tangential direction. Again, I apply a force perpendicular to velocity. This is the new position of the box. Again, the box is moving with the velocity v in vertically downward direction and I apply a muscular force in horizontal direction. This brings us to a new position of the box with a velocity v in left direction and we apply muscular force perpendicular to the velocity. This creates the positions of the box as shown in the figure. If we see carefully, the force is always perpendicular to the velocity. Force and velocity are perpendicular. Here also force and velocity are perpendicular. Here also force and velocity are perpendicular. Here also force and velocity are perpendicular. So at each position, force and velocity are perpendicular. And the force is always directed towards a single point. This point is known as the center of the circle. Because this force is always pointing towards the center, hence it is known as centripetal force. Thus, centripetal force F subscript C, C stands for centripetal, equals mass into acceleration by Newton's law. Force equals mass into acceleration. Thus, centripetal force equals mass into centripetal acceleration. In this example, the muscular force of the hand acts as centripetal force. What is centripetal force? Centripetal force is force directed towards the center. Examples of centripetal force. The first example is of the box. The motion of the box was in this direction. The velocity of box is in this direction. The muscular force of the hand is in this direction. The velocity and the muscular force are perpendicular. If we see carefully, force is perpendicular to velocity. At each and every point, force, velocity, force, velocity, force, velocity. At each and every point, force is perpendicular to the velocity. Hence, the box moves in circular motion. Here, the muscular force of the hand acts as centripetal force. In the example 2, the circular motion of Earth. The sun is always attracting the Earth towards itself. The velocity of Earth at this point is in tangential direction. The gravitational force is perpendicular to the velocity. At each and every instant, the force is perpendicular to the velocity. Hence, Earth moves in circular orbit around the sun. Coming to our final example of motion of electron. As we all know, the electron moves in circular orbit around the nucleus. This is the nucleus. The nucleus always attracts the electron towards itself by electrostatic attractive force. At this point, the velocity of electron is in tangentially rightward direction. The electrostatic force of the nucleus is perpendicular to it. At each and every point, the velocity of electron and the force are perpendicular. Hence, in this case, electrostatic force of the nucleus on the electron acts as centripetal force. From all these three examples, we infer that the condition for circular motion is force should be perpendicular to velocity at each and every instant. At every instant, the force is perpendicular to the velocity in each and every example. Secondly, the force is always directed towards a single point known as the center of the circular path. Here, the sun is at the center of the circular path. Here, the nucleus is at the center of the circular path. These are the conditions for circular motion. Force should be perpendicular to velocity and the force should always be directed towards a single point known as the center of the circle. This is all about centripetal force. In this concept, we will study centripetal acceleration. To study centripetal acceleration, we need to remind ourselves about centripetal force. Centripetal force is mass into centripetal acceleration. Accordingly, centripetal acceleration can be defined as the acceleration produced due to centripetal force. The direction of centripetal acceleration is same as that of centripetal force, which is towards the center. Hence, the direction of centripetal acceleration is also towards the center. Moving on to the expression for centripetal acceleration. Centripetal acceleration is equal to omega square r, which is nothing but v square by r, where AC denotes centripetal acceleration, omega denotes angular velocity, and r denotes the radius of circular path. V stands for velocity of circular path. This expression needs to be remembered. Now, how to derive the expression for centripetal acceleration? There are two methods mainly. One is by dimensional analysis and another is by using vectors. In this derivation, we will go by dimensional method. For using the dimensional method, we are given centripetal acceleration depends on angular velocity and radius of circular orbit. Thus, centripetal acceleration depends on omega raised to x and r raised to y. Writing the dimensions for accelerations, angular velocity and radius, we get the dimension of acceleration as L1 t raised to minus 2. The dimension of omega, angular velocity, which is angular displacement upon time, which is 1 upon time, which is t raised to minus 1. The dimension of radius, radius is nothing but length. Hence, the dimension of radius is length raised to 1. Substituting the dimensions of acceleration, angular velocity and radius in the expression which we got, we get L1 t raised to minus 2 is equal to t raised to minus 1 raised to x, L raised to y. Therefore, L raised to 1 t raised to minus 2 equals L raised to y t raised to minus x by simple mathematical rearrangement. Comparing the two equations, the powers of the two equations, we have the power of length here as 1 and the power of length here as y. Hence, y equals 1. Similarly, the power of time here is minus 2 and power of time here is minus x. Hence, x equals 2. Thus, comparing, we get x equals 2 and y equals 1. Substituting the value of x and y in our original expression of centripetal acceleration. Centripetal acceleration is omega raised to x r raised to y, which becomes upon substitution as acceleration centripetal equals omega raised to 2 and r raised to 1. Using further v is equal to r omega. Therefore, omega equals v by r. In this given expression, omega square r, we get centripetal acceleration is omega square r, which is v by r the whole square into r. Cancelling off the r, we get the expression of centripetal acceleration as v square by r. Thus, we have derived this expression for centripetal acceleration as omega square r and v square by r using dimensional analysis. Also, we will study the derivation of centripetal acceleration by vector method in our later part of the topic.